So, classification of matter. Hopefully the video yesterday, I think it's really kind of cool. You guys are really good, like finding those patterns and things from the brain game. So classification is pretty easy because you're grouping things by characteristics, by properties, and so we're going to look at those. We already looked at density, obviously, but we're going to be able to identify things based on those characteristics and property, and then be able to put like things together, keep different things apart, and just use it as a way to kind of organize all this stuff that's around us in our daily life. Okay, so we know that matter is anything that has mass and takes up space. That's the definition. Basically everything except for energy is matter. So energy like light, sound, thermal, which is heat, nuclear, those are all forms of energy. And so basically that's the only category of stuff in our world that is not considered to be matter. Okay, is it important? Sure, it matters, but it's not matter. So anything that has mass and takes up space. And so all of those things technically have a volume too, because that's the definition for what volume is, how much space something is taking up. That's what density is, because that's mass and volume are the two characteristics. So all of these things are going to have some form of density to them. All right, so one way of classifying or organizing is to decide what state it is in. And by state, we mean like solid, liquid, or gas. So not like, is it in Colorado? Is it in California? Is it in Idaho? Right? We mean the state of matter. We're going to have an entire unit on that, just because it makes this unit just kind of drag on too long. So we're going to have our own separate unit, just like we did for density, because it's so important. States of matter are also very important, and there's a lot of characteristics that go with just identifying is something in the solid, liquid, or the gas form. And so we'll have a whole unit on that. Okay, so deciding what state something is in is not the only way. It's a big way of identifying or classifying, but it's not the only way. So that's what this unit's going to be about, all of those other ways to classify things. First one we're going to start with is physical properties. So identifying those physical characteristics that are unique to a certain state or a certain type of material. So some of the examples for physical property are color, odor, hardness, density, conductivity, like so does it conduct electricity or not, size, shape, viscosity, malleability, boiling, and melting points. And we're going to get into those. Some of them, obviously, color, okay, we really don't need to worry too much about that. It's pretty self-explanatory. But we'll get into some of the others that maybe are a little bit unfamiliar. The other way that we can classify things is by looking at it chemically, right? How does it react? And we already have a pretty good idea of this, why things react and why some don't, because of our units on the periodic table and our chemical bonding unit. And so basically, what is it going to react to or with? How reactive is it? So like our alkali and alkaline metals and our halogens are very reactive because they're so close to having that outer valence full. Our noble gases, right, they just sit there on their donkeys and don't do anything because they are already stable and satisfied. They don't want to change. So what we already have learned is going to kind of play into this a little bit in the second way of classifying. And then finally, what is a substance made of? What is it, right? Is it a pure substance? Like, is it all one thing, or is it a mixture of multiple different things? Okay, so I have a container that has all peanuts in it. That would be considered a pure substance. If I have a thing of trail mix that has peanuts and maybe pretzels and M&Ms, like a variety of different things, that would be considered a mixture. Right, so we're going to look at those different combinations. There's also, we'll talk about heterogeneous and homogeneous if we're talking mixtures. Is it a solution? You probably noticed from your vocab that there are a ton of S words like solute, solvent, solution, saturated, supersaturated. And so we're going to have lots of ways to help kind of keep all those words straight. But I don't know, probably about almost 10 of them are S words, which is kind of coincidental. But we'll find a way, like I'll give you ways to help keep all those straight as we get to that part in our unit. And then if we do have a mixture, how do we separate that mixture into its individual components? So how would we do that? What kind of properties could we use to separate it out? And we're gonna have a lab that you'll do this. You're gonna get a container that's gonna have a mixture of different items. You're going to have to get them separated out. You can't just reach in and be like, oh, I see that marble, I see that, I see that. You can't just reach in and grab it. You're gonna have to use different properties and explain to me how you got that mixture separated into its individual kind of pure substance categories, right? So we'll get a lot of practice with this. So far, so good? I told you it's a pretty easy unit to kind of ease our way back into the new year. All right, so we're going to start with physical properties. So this is any characteristic that can be observed or measured without changing the identity or the composition of the substance. So anything where it is basically not altering the chemical makeup is going to be something that is a physical change. Okay, so if I take this piece of paper, I rip it in half. It's still paper. It's just a different size and a different shape. Nothing about it has changed except for that, right? What this is made up of is exactly what this is made up of. There's just, it's a smaller piece now, right? This is a physical change. I've changed its size and its shape. I haven't changed what this is chemically. Now, if I would burn this paper, is it gonna be the same as this? No, right? Those ashes that form when I burn this are not going to be the same as what this paper was. So I can rip it in half and change its size and shape. Burning is always a indication that a chemical change has taken place. Can't undo that. I can't unburn it, turn the ashes back into paper. It'd be pretty amazing if I could do that, but I'm not that good. It's not possible. All right, so if you think of it like that, that's always like kind of a nice go-to example. Anything that doesn't affect what the item is actually made of. And some of them are really straightforward. There's a few that people are like, wait a minute, that seems like it'd be a physical, or that seems like it should be chemical, and it's not. And we'll talk about some of those exceptions later on. But remember, we had physical weathering in 8th grade. And I had a few of you in 8th grade, but you had this with Mr. Archie, even if you weren't with me. Physical weathering, right? It is things that are breaking down rock into smaller pieces. It's not changing what the rock is made of, but it's just making it a smaller piece of that same rock. So taking a big boulder and it's splitting in half, that would be considered physical weathering. So that idea of physical weathering and physical properties and physical changes are pretty related, because it's just changing the size, shape, color, but it's not changing what it is you're dealing with. All right, so we talked like plants burrowing, roots like splitting into rock. We talked about frost wedging, right, where water gets into cracks and then freezes and expands and makes that rock break up into smaller pieces, kind of like what's happening on our roads right now. You get a little crack in the asphalt, water gets in, it freezes, it expands, it makes that hole bigger and bigger and bigger until we have big potholes that we're dodging and sometimes not dodging and bouncing around, right? And so a lot of what if you think back to that unit from last year, which is always kind of weird because we're actually doing it right now in 8th grade science, so the timing always matches up good in here, for me at least. But if you think back to those things, those same ideas with physical weathering, you're still not changing. If you have a big boulder and it turns into a tiny pebble or piece of sand, it's still the exact same material, it's just a lot smaller, right? And so that same concept is true here. We're not changing what it is that we're dealing with chemically. So some examples: size, texture, shape. So even like, let's say I have a board and I take a piece of sandpaper and I sand down the rough edges. Well, the little sawdust that forms is still chemically the same as the big piece of board, right? So I'm just changing that texture, going from rough to smooth. You can even, so color, and sometimes people are like, whoa, whoa, whoa. sometimes can be funny, like sometimes people are like, I don't think that could be a physical change, it's probably chemical. But if I have a wall and I take paint and I put paint on it, it's still the same wall underneath it, I've just changed the color of it, right? So obviously the color adds some chemical, but they're separate. Like I can peel that paint off and it's still the same wall or the same board or the same, drywall underneath, okay? Boiling point and melting point we'll talk about. These are unique and specific to, like you can look up the boiling and melting points. All right, we'll talk about those more in a minute. Malleability, hardness, conductivity, viscosity, density, we've already talked about, and magnetism. We'll talk about those a little bit more in detail. Last year, you had magnetism 2 or 3 different times within our units, so probably have a pretty good idea of those as well. Okay, so we're gonna look at these all in a little bit more detail. So the boiling point. This is the temperature, it's a set temperature that something will vaporize and become a gas. So this is a phase change, going from a liquid to the gas version. In Fahrenheit, what temperature does water boil? Anybody know? The boiling point of water. And I usually have 1 or 2 people that know.
210 degrees.
Very close. Were you guessing?
Yeah.
Really?
Well, I kind of know, like, around that, but I don't know.
It's 212. Good. Did you just say that?
Billy had it.
Billy had it. I'm sorry, Billy. I robbed you of genius.
Billy.
Jeez. 212. Well done. All right. So 212 degrees Fahrenheit. Anybody know what that is in Celsius? And this is a much easier number. Billy. Very good. Okay. Good. I feel like I didn't rob you now. So 212 degrees Fahrenheit or 100 degrees Celsius. These are going to be numbers that are important as we get to states of matter next unit, because we can actually measure these temperatures, and at that, as soon as it reaches that 0 degrees Celsius or 212 degrees Fahrenheit, boom, it should start boiling, okay? So different materials, different substances have a different boiling and melting point. And so we're really, water is so dominant in our society that most of what we think, we're like, oh, everything is going to boil at 212 degrees Fahrenheit, and that's not true at all. On some periodic tables, they even have some of these things, like on the little tile, it actually has the BP and the MP for boiling point and melting point. Some are very low, so like at room temperature, they boil, right? Which would be really crazy, like if I have my cup of water and it's just sitting on my desk boiling at room temperature. So we relate everything to water just because it is so prevalent in our world, but not everything is going to boil at or even close to that. And so we'll look at a few of those examples later on throughout the year too. Melting point is kind of the reverse. Instead of heating something up like we do to get it to boil, we are taking energy, that heat energy away, and so we're getting something to melt. So going from a solid now to a liquid, and honestly, like, it depends on like your point of view, because you could also have a liquid going to a solid and that'd be the freezing point, right? So it's just kind of like, which direction are you looking at it? The temperature itself would still actually be the same. What is that magic number that we hope for in January and February so that we maybe could get school canceled? What is that freezing point that we're so excited about? Caden? 32 degrees, right? And so like, I know I was scanning the other day, like looking ahead at the forecast, I'm like, okay, we're gonna get down into the 20s and, here, the next couple nights, it's like, well, maybe, right? But then there's no precipitation, so it doesn't help us, right? So the freezing point and the melting point typically are the same temperature. It's just like, which direction are you going? Are you warming it up at the melting point, or is it getting colder like for the freezing point? But the point or the temperature itself is the same. Again, it's just like, which direction are you thinking of it? So here they're saying warming it up, the melting point, the temperature where a solid will turn into a liquid, but it is technically the same as a liquid freezing and becoming a solid. Anybody know what that is in Celsius? So it was 32 degrees Fahrenheit. This is also a very nice, easy number, 0. So 0 for freezing, 100 for boiling. That's handy, right? Those are easy to remember. 32 and 212 are not as friendly, right? And that's part of the reason that like the international system of measurement is just a little bit nicer and easier than ours. We're used to ours, but the metric system and the SI system are much more practical. 0 and 100, much nicer. Okay, so malleable or malleability. It's the ability of metals typically to be formed, shaped, beat on, hammered, and they're not gonna bust and break. If you take, like think if you take an ice cube and you take a hammer and you whack it, right? It's gonna shatter, right? If you take a piece of copper and you take a hammer and you start pounding on it, it's not going to shatter. It's going to just start flattening out. And so malleability is the capability of materials, typically metals we're talking about, to be able to take the shape or the form that you're giving them, right? So not necessarily melting them down doing it, but being able to like hammer them out, you know, and not break or shatter. So typically, like aluminum can be this way sometimes, copper most definitely. And so for different, depending on what you're needing, right, that can be really important. Now, would it be good to use that material like to have like real strong support like in beams or things? Probably not. But you know, there are reasons why we want to be able to shape our metal. So lots of different natural things, you know, minerals, rocks, have different degrees of how hard they are. We call that hardness, which is pretty easy to remember. So it's on a scale. Talc is the softest, and then diamonds are the hardest, right? And then from there, it's just kind of a comparison. And you probably did this in 6th grade, I'm guessing, if I'm remembering right, with Mrs. Radel. You can, like if you have an unknown rock and you're trying to determine what rock it is, you could tell like if the fluorite would scratch the rock, then you know that it is softer, right? And then if the apatite doesn't scratch it, then you know that, you know, your rock that you're trying to identify is gonna like fit right in here. So like if it'll scratch one but not the other, that's kind of like where it would fit. And then from there, you could look up known rocks that are in the scale between 4 and 5. And so you're able to kind of figure out by process of elimination, like, okay, what could this rock possibly be? And so this scale helps you with identifying unknowns. And so we call it like the scratch test to like, and if talc is so soft that it will mark on everything, right? It comes off on everything. Diamonds will scratch everything. Like it's never going to be what gets scratched, if that makes sense. So this is another way, not something that we're going to deal with a whole lot, but it is a physical property. You can look up the hardness of lots of rocks and minerals, and it can help you identify and group them. All right, so conductivity. How well does a material allow electrons to flow? So obviously copper is one of our #1 most conductive materials. And so obviously in electronics, in wiring, you're gonna have a lot of copper. Copper is pretty expensive, and that's like, I know, you know, a lot of people worry about like if you're building or you're doing something with copper. Copper is something that a lot of people try to break in and steal because they can take that copper and try to resell it, and it is expensive. So it's not that it's like diamonds where it's like rare, it's just that it is expensive. And so, you know, unfortunately, sometimes people like to try to, you hear about that a lot at least. You know, like somebody building a house or building something and somebody comes in, and if it's not secure, like they come in and try to strip out things and take the copper. And so like I said, in electronics, where you want those electrons to be able to flow pretty easily, you're going to have some material that's going to allow that to happen. And typically you're going to be using copper. Okay, so viscosity. This is one that you may or may not. Has anybody heard of the word viscosity, or something is viscous? Yeah? Where have you heard it? Just remember the word sounds familiar. So the only place that I can think of in everyday life where I've heard this is with motor oil. Like it has you'll hear them on a commercial say that it has, such and such viscosity or a high viscosity. Viscosity means like how sticky and how thick it is. So if you think of like water compared to honey, well, the honey is a lot more viscous. It's thicker, it sticks to itself as you pour it, it kind of like flows slowly and like flows over itself. The water just pours out really quickly, right? So motor oil is meant to coat the moving parts in your motor. So the more viscous it is, like you don't want it to be like sludge where it can't get those parts to move, but you want it to have like that nice greased ability where it's able to keep those parts from rubbing and causing a lot of friction and causing a lot of heat. So it's trying to coat all of those moving parts. So you want it to have just the right balance where it's not too thick of a viscosity where those moving parts have to work hard to work against it, but you don't want them rubbing on each other like where there's no barrier, because then you get a lot of friction, you get a lot of heat, and then that's when those moving parts in your motor can lock up. So you have to have that balance. So viscosity is like the flowability, the stickiness of an object, typically going to be a liquid. And so for different motors, they recommend different viscosities. So, just kind of have to pay attention. But I can't think of any other situation where I've heard the word viscosity used, besides that motor oil idea, which is kind of practical. I mean, at some point you guys are all going to be driving legally. And like my son, he's home for a break right now, and he went and got stuff to change his oil, and he always takes care of that, like when he comes home random. So you gotta keep up with like that maintenance kind of stuff. Okay, color. Hopefully I don't need to say any more about color. Odor. Okay. So, again, pretty basic. And if you're noticing, a lot of these are dealing with our five senses, right? Sight, smell. And then finally density, which again, we had our whole unit, so it's nice that we've already covered all the big stuff with density, so we don't have to get into that detail, but it's the amount of mass in a given amount of space, which again, kind of matches the definition of what matter is. So everything that is matter is gonna have a density of some sort. Mass divided by volume. And then finally, magnetism. And so, is the object influenced by the magnetism of other objects? So, not everything is going to be magnetic, obviously. If the domains within a certain object, usually iron, nickel, and cobalt are going to be magnetic metals. Those domains are all lined up facing a certain way, and that's why that's magnetic. And if the domains are kind of all pointing different directions inside those little atoms, then you're not going to be magnetic or have magnetic objects. So we're going to go ahead and stop there, and then we will pick up tomorrow with chemical changes and properties.